All right, ladies and gentlemen, if I could have your attention up here at the screen. So today we look at simplifying radicals. I hope that you have all seen this before, but if not, that's why we're reteaching it in the prerequisite chapter. You do need to know how to simplify radicals because next week we're going to learn how all radicals are actually bases with fractional exponents. And so then we're going to use what you know about radicals and your rules of exponents and put it all together. So let's go back. But the first thing, can we put our phone away? I know it's the end of the day. If it's a temptation for me, I always just have to put it away from me, especially at the end of the day on the Friday. If we could just put that, there's going to be probably some piece in here that could be new. Let's review what the terms are in a radical and what I might be saying, and you want to know, what am I referencing? If I give you the cubed root of -8, well, the first thing that maybe let's start with is, what would be the answer there? What would be the cubed root of -8? We did this on the bell ringer. Annalise. -2, awesome. And the reason being is because you have an index, I will be using that word a lot, because you have an index of 3, you are looking for 3 of the same number that when multiplied, in fact, I should probably change it to like this, gives you the number underneath the radical. That little index is called your index, or sometimes it's called the root. I might use that word interchangeably, so make sure you know that's what I'm referencing. The radical sign, you guys know what a radical sign is. This number underneath the radical, it's called the radicand. I don't use that word a whole lot, but in case I do, that's the number that I'm referencing. And that's an example of a radical that you're simplifying. Now, I want to ask you another question that you probably were taught in Algebra 1. If you were asked, what is the square root of 16? What would be your answer? 4, okay? Nice, the answer is 4. Now, did you know that there's actually an invisible index of 2 for all square roots? Okay, awesome. If you didn't know that, that's your learning point. And then the reason that we know it's 4 is because if there's an index of 2, we're looking for a number times itself. So we're looking for 2 of the same values, which will give us the number on the outside. Now notice none of you gave me the answer of -4, which is correct. The answer is +4. Why is it +4 when you know that -4 times -4 is still 16? The reason it's +4 is because if you're given a black printed radical sign, it's understood to be the principal root. Go ahead and write that. This radical sign is called the principal root. Have you guys heard that word before? Principal root? If you haven't heard it, I may have heard it when I was a student, but I really didn't understand what it meant till I was a teacher. A principal root means it's asking for only the positive answer. So the principal root equals give the positive solution. So your algebra teacher taught you well. The answer is 4 there. Now, when we're in an equation in Algebra 2 and we ourselves use a radical as a tool to solve, we're going to have to think about the plus or minus answer. All right, that's going to come into play later in the lesson. So right now, let's go ahead and jump in to simplifying radicals. In simplifying radicals, you can really use one of 2 methods. I'm going to show you both. You can decide which one you like. To be honest, I use a combination of the 2. So there's not really one that's more helpful than the other. There is one that is typically faster. Number 1, if I asked you what's the square root of 144, what would be the answer? 12, good. You're using method 1. Method 1 is you know your perfect squares. The square root of 144 is just equal to 12. Method 2 would be if I don't know what the square root of 144 is, I would factor it down. So method 2 really requires factoring. And if I'm looking for the square root of 144, I would break that down. I could go all the way down, or as soon as I find 2 of the same factor, since it's a square root, an index of 2, Once I found two of the same number, I know I can essentially like group them together and take it out because 12 times 12 creates a perfect square. So the square root of that becomes 12. Now we're going to use maybe a combination of the two. Hopefully you'll feel comfortable by the end. Number 2, does anybody know what the square root of 225 is? Oh, a few people do. Michael, what is it? It's 15. Now, what if you didn't know the square root of 225? Then you could use method 2. You could factor 225 down. What do you know goes into 225? 5, it's 5 and 25, right? No, 5 and, I know it goes into 5. I might need my calculator. 225 divided by 5 should be 43? No. What is it? 45? Thank you. I'd have to get my calculator. That's all good. So 5 and 45. And then if I break down 45, what goes into 45? 5 and 9. And then if I break down 9, what goes into 9? 3 and 3. Now, if I get to the end of my factoring tree and there's a lot of factors at the end, I might want to line them up just so I don't forget any. What we did is we used the prime factorization. The square root of 225 factors all the way down into 3 times 3 times 5 times 5. Because it's a square root, as soon as I find 2 of the same number under the radical, I found a perfect square and I can take it outside of the radical. What else can I take outside of the radical? 5. I would multiply them, and then what's 3 times 5? 15. So if you didn't know method 1, you would just use method 2. Number 3, you might use method 1. Does anybody know the cubed root of 27? Jack? 3. So Jack would use method 1. He knows that 3 times 3 times 3 gives me 27. If I didn't know method 1, I would factor down 27. I know that 3 goes into 27. It's 9 times 3. 9 is 3 times 3. So 27's prime factorization is 3 times 3 times 3. Based off of the index, how many of the same factor do you need before you can take it outside of the radical? 3. You need 3 of the same factor. So I have 3 here, 3 times 3 times 3, so I can take that out, and that answers 3. Number 4. Number 4, the cubed root of 125. Does anybody know the cubed root of 125? Okay, if you know it, you can write it down. If not, use the factoring tree. But go ahead and try this on your own. I'm going to walk around, see if you need help with it. Just see if we get to that answer. And I need to freeze that. There we go. Calculator. A lot of us know 5 goes to 125. 5 times 25. All right, guys, I saw some of us use the prime factorization or factoring it down. I saw some of us just know the perfect cube of 125, or that 125 is a perfect cube. So the cubed root of 125 would be 5, but that should be your answer, 5. Any questions on that? All right, let's move on to number 5. Number 5, the square root of 300. If you're using method 1, does anybody know the highest perfect square that would go into 300? Method 1. So let's think about perfect squares. 4 is a perfect square. 16 is a perfect square. 25 is a perfect square. 36 is a perfect square. 49 is a perfect square. 64 is a perfect square. 81 is a perfect square. 100 is a perfect square. 121 is a perfect square. Out of those numbers, what is the highest perfect square that goes into 300? 100. So if I'm using method 1, I would say that 300 is the result of the square root of 100 times the square root of 3. What is the square root of 100? What's this? 10. So if you know your perfect squares, you would use method 1. If I didn't know that, I'm like, oh, I forgot that 100 was the highest perfect square that goes into it. What else could I do? Factor it down. 300, well, now I know it's 100 times 3. 100 is 10 times 10. I could keep going, but once I find 2 of the same values, if it's a square root, then I don't need to keep going. So this is a square root, so I know I need 2 of the same factors. And so I have a 10 square root 3 as the answer. All right, number 6. Well, let me stop for a moment. Any questions on that? All right, number 6. 6, I've talked a little bit here. So why don't you turn to your partner, the person with the, we've done most pets, we've done most siblings, the person with the tallest person in the group. So you might have to stand up. The tallest person in the group. You start this. You start. Oh my gosh. Lucy, I think you're a little taller. Yeah, like a fraction. Like a fraction. All right, ladies and gentlemen, if you could bring your attention up to the front. If you did this using factoring, if you're factoring all the way down, maybe line up your factors at the end just so you don't lose any. 108 factors down into 3 times 3 times 3 times 2 times 2. Since this is a cubed root, I need how many of the same factors before I can take it out? 3. So I see 3 times 3 times 3. I can circle that, cross it off, bring it out to the front. And the answer is 3 cubed root of 4. If you knew your perfect cubes, the method 1 route would be 27 goes into 108 evenly. And so that would be 3 times the cubed root of 4. All right, any questions on this so far? Let's try number 7. Number 7, how many of the same factor do we need before we can take it outside of the radical? 5. This is a 5th root. So I need to either find a perfect power of 5. I don't know my perfect power of 5s. I know 32 is 2 to the 5th. I think that's the only one I know. So what should I do if I don't know? Factor it down. What do you know goes into 96? 3. It's 3 times 32. Good. What goes into 32? 8 and 4. What goes into 8? 4 and 2, and then 4 goes down to 2 and 2. And 4 goes down to 2 and 2. Now, notice all of these at the bottom of the tree, it might look messy. So I like to line it up so I don't forget anything. Now, how many of the same factors do I need before I can take it outside? 5. What number should I take outside of the radical? 2. Good. So this would be 2 cubed root of 3. Now I could have done this using method 1 just because I know 32 is a perfect power of 5. So I would break it up as the 5th root of 32 times the 5th root of 3. but that's not the more common way that I've seen this done. So I'll just stick with that. A 3, because
Yeah, why is it a 3? No, you put cube.
oh, thank you. I'm like, oh, what did I do? Okay, sorry. Thank you. It's the 5th root of 3. Thank you, Jonathan. There we go. Does that look right? Yeah. Okay. All right. We're good. 2 times the 5th root of 3. All right. On to the next one. What if there are variables in the radical? Same thing. Let's think about what we have been doing using method 2. Method 2, we were factoring it down. If I factor down 50, 50 is 25 times 2. 25 is 5 times 5. So if I think about the square root of 50, I could write 5 times 5 times 2. If I'm writing out x to the 6th, or if I'm factoring it down, how many x's are in x to the 6th? 6. So I would have 1, 2, 3, 4, 5, 6. How many y's are in y to the 9th? 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, out of the numbers, what should I take outside of the radical? 5. Good. Because it's an index of 2, so I need 2 of the same factors. 5 times 5 is 25. That's a perfect square. So I'm going to take it outside. Now, if I'm looking at the x's, I need 2 x's. I need a pair. And how many pairs of 6 x's are there? 3. 1, 2, 3. So I could take out an x, and an x. What could I simplify that to? X times x times x is just x cubed. Good. X cubed. Now, if I ask you how many sets of 2 are there in 9 y's, you could just circle them, or you could tell me how many sets of 2 are in 9 y's. 4. So I'd have y to the what on the outside? 4. So now if I kind of clean this up and see what's left under the radical, I have a 2 and a y. So I would call this 5x cubed, y to the 4th, times the square root of 2y. Does anybody see a faster way we could have done that rather than writing out all of those x's and all of those y's? Ooh, a few people see it. Turn to your partner and see if you can tell them what's the faster way. Weston, Finn, do you guys know? Divide by 2. So take the index, right? 6 divided by 2 would give you 3, right? And 9 divided by 2 would give you 4. And then there's a remainder of 1. So we've got that 1 on the inside. Nice. All right, guys. Does anybody, I'll give a road excellence for this. Does anybody feel like they could explain what you could have done faster? Asher. Why did you divide it by 2? Ooh, so divide the exponent by the index. The answer goes on the outside and the remainder goes on the variable on the inside. I like that. Okay, so let's just write that. I'm going to use Asher's vocabulary. Take the exponent, divide it by the index. So I'm going to say divide the exponents under the radical by the index. And then I'm just going to go ahead and point. That would be your answer. So in this case, the 6 divided by the 2 gave us a 3. But in this case, the 4, we would take 9 and divide it by 2. And that is our answer. So our answer goes here. But what if 9 divided by 2 is not 4? It's 4 with a remainder of 1. So your answer goes on the outside. So I'm going to say answer goes on the outside, but I'm going to show the remainder is on the inside. If there is no remainder, there won't be anything left on the inside. All right, let's try that with, well, actually, before we can move on, I need to talk about something. This is kind of a deeper level concept. I told you guys that the radical is the principal root, correct? Principal root means you're asking for the positive solution, and really it's when you're working with an even power. When you have an even power, if you're working with variables, you have to show the reader that the variable could not be negative. So this x cubed, I'm going to have to put absolute value symbols around that, because let's say x was -1. What's -1 cubed? What's -1 times -1 times -1? -1. Can I get a negative number outside of an even radical? No, I can't, because an even radical, like the square root of 16, is a +4. I can't say -4. So the moral of the story, if you're like, well, when do I need to use a radical? If you're taking an even root, if you have an even index, also known as an even root, when you have an even index and the exponent on the outside has an odd power, you need to put absolute value marks around it. Let's write that. So the book explains this as well in case you want to look at the book, but that's essentially really what you need to know. When you have an even index, or if you want to call it a root, you have an even root. What did I say last class? Let's say when you take. So when you take an even index or root and you have an odd exponent on the variable, you need absolute value symbols. So notice I have the absolute value around the x to the third because it was an even root and I had an odd exponent on the variable on the outside. So I have to put absolute value to say, hey, no matter what x is, if x was -1 or if it was +1, when you cube it, you need to have the positive solution. You don't have to do that with numbers because they already are positive. And you don't have to do that with even variables because any negative number to an even power produces a positive solution. Deeper concept, but it's important to note. And when you check your answers, either in the back of the book or the ones I provided, there will be certain absolute value symbols. Michael. Yes. You could put it right next to it, like the x times the y has to be absolute value. That would notate that your answer has to be positive.
But you could have it all in one.
Yes. All right, on to number 9. Number 9, let's work through this. The 24, we might want to factor down. 24 is really what goes into 24? 2 and 12. 12 is 6 and 2. 6 is 2 and 3. If you know your perfect cubes, you might know 8 goes into 24 evenly. If I'm using the factoring tree, what am I going to take outside of the radical? A 2, good. So I have 2 cubed root of what's left under the radical? 3. And now let's use that trick that Asher explained with the variables. What is 7 divided by 3? 2, but there's a remainder of 1. Where does that remainder go? Inside the radical. Okay, let's try it with the b. What's 12? 12 divided by 3. 4. So I'm going to have a b to the 4th. Are there any remainders? No. So that would be my answer. 2a squared b to the 4th cubed root of 3a. Then I want to check, is this an odd index or is it an even index? Odd. So do I need to do anything with absolute value? Nothing. All right, on to number 10. Number 10, the 4th root of 32a to the 7th b to the 12th. Let's go ahead and factor this down. 32, what goes into 32? 2 and 16. 16 is 8 and 2. 8 is 2 times 2 times 2, or 4 times 2. So I have 32 consists of 5 2s when you factor it all the way down. How many do I need before I can take it outside of the radical? 4, because it's a 4th root. So I have 2 times 2 times 2 times 2. So I'm going to take that to the outside. And then I have the 4th root of how many are left underneath? What's just a 2? And then I want to make sure we understand Asher's trick. So turn to your partner and see if you can determine what the variable answers will be. Oh, sorry, go ahead, Riley. Sorry, I'm thinking it was directed towards me. Go ahead, explain it to Lucy, I'm sorry. All right, guys, bring it up to the front. If you have the correct answer, you should have 2 times AB cubed times the 4th root of 2A cubed. That should be what your variables and numbers consist of. That's not the full answer, but I want to make sure we understand this trick. Remember, A to the 7th means you have 7 A's. When you're looking for a 4th root, you need 4 A's before you could take it outside the radical. So I can group one set of 4. So I have an A to the 1st on the outside, and then I have 3 A's left inside. Should I have absolute value in this case? Is it an even root? Yes, it's even. So that means, ooh, I do need absolute value. When the variables have what type of exponent? Odd. So this and this should have absolute value around it. You could have 2 absolute values, or you could just have 1 around it to group them. But you do need absolute values when you have odd exponents. So this is an odd exponent. All right, last one, number 11. Number 11, go ahead and try that one on your own, and then we'll check our answer. Okay, check up here when you're finished. Did we need absolute value? Oh, there's a reason why we don't need absolute value here. Does anyone know why? The index is odd. If you have an odd index, like the cubed root of 27, it's either 3 or the cubed root of negative 27 is negative 3. We don't need any absolute value. It's only when you have an even root that you have to think about that principal root situation. All right, give me a thumbs up if you got that. All right, pretty good. Side ups, ups. Okay, hopefully we'll have more and more practice as the days go on. We'll feel hopefully really confident on this. On the lines of radicals, let's make sure we know what we can and we cannot do. What's true and false. So number 10, If you are adding square root of 9 plus 16, can you break that apart to square root of 9 plus square root of 16? No. In other words, if you're checking this, is the square root of 25 the same as 3 plus 4? No, 5 is not equal to 3 plus 4. So this is false. You can't separate those radicals. What if it's subtraction? Can you subtract and then separate the radicals? Subtraction is very similar to addition. So no, this would be false. You can't separate that radical. Number 12. Is the square root of 64 the same as 2 times 4? What's the square root of 64? 8. And what is square root of 4? 2 times 8. Wait, 2 times 4. Sorry. I was going to say, this should work. What's wrong? But that's because I did the math wrong. So yes, that is true. You can separate when it's multiplication. Can you separate when it's division? Yeah, you can do that too. So you just cannot separate the radical when it's addition or subtraction. Also, along the lines of adding and subtracting radicals, we want to make sure we know what are like radicals. And because you guys came from geometry, I'm going to use a geometry illustration to show how to add radicals. Actually, I'll ask for your help. If I look at this small little triangle, this is an isosceles right triangle. If the legs are congruent, there's something that's true about the hypotenuse. Does anyone know what the hypotenuse would be here if the sides are 1? Jonathan? Nice, 1 root 2. If I look at the medium triangle, what would be the value of y then? If the sides are both 3? Annalise? 3 root 2. If I look at the big triangle, this part is 1, this part is 3. So what's the length of the entire leg? Yep, 4. That means this leg is also 4. So what's the length of this hypotenuse? 4 root 2. This hypotenuse is what x plus y equals. So that just illustrates how to add radicals. 1 root 2 plus 3 root 2 equals 4 root 2. Moral of the story, you need like radicals. They have to have the same number under the radical and the same index, and then you add the coefficients in front. So that's the key components to adding and subtracting radicals. The number under the radical must be the same. The root must be the same. You're going to add the coefficients, but leave the radical the same. So let's look at example 1. Example 1, they have the same index. They're the same roots. They're both square roots, but do they have the same number under the square root? This is 32, this is 200. Not the same, but can we simplify them? Yeah, we can simplify this. Let's use method 1. 32, what's the highest perfect square that goes into 32? 16. It's 16 times 2, which would be 4 root 2. The highest perfect square that goes into 200 would be 100. Square root of 100 is 10. What would be 4 root 2 plus 10 root 2? 14 root 2. Number 2. The indexes are the same, but the numbers under the radical are not the same, but we can simplify. Let's use method 1. The highest perfect square that goes into 24, or the highest perfect cube, excuse me, that goes into 24 would be 8. It's 8 times 3. What is the cubed root of 8? 2. So this would be 2 cubed root of 3. What do I do with this number 4 on the outside? Multiply it. So this middle radical is going to simplify to 8 cubed root 3. The radical on the left is going to be 2 cubed root 3. Minus, you could use factoring tree, or if you know your perfect cubes, the highest perfect cube that goes into 81 is 27. It's 27 times 3. So the cubed root of 27 is 3. So this would be 3 cubed root 3. Now I know I did that using a different method than the factoring tree. I just want you guys to see that they both would work. So now I have 2 cubed root 3 plus 8 cubed root 3 minus 3 cubed root 3. Now, can I combine all of them? Yeah, they're the same radical with the same index. So 2 plus 8 gives me 10. What's 10 minus 3? Yep, so that would be our answer, 7 cubed root of 3. I like to think of these as just an x. X represents any number, any real number. 2x plus 8x minus 3x would give me 7x. That would be it. All right, number 3 and 4 are online. If we don't get to them, you can try number 3 on your own. Or you could look up here. Lucy. Why is what? It's the largest perfect square that can. 121 doesn't go into 200 evenly. I guess I should be more clear because 200 divided by 121 is going to leave a decimal, and you're looking for the highest perfect square that goes into the value evenly. Oh, the group work, I'm going to change the due date since we didn't get a chance to correct it. So just hold on to it and then we'll submit it when we have that time to correct it. Thanks, Asher. Ah, Lucy, wonderful.
Yeah.
All right, let me stop sharing this.
What's happening?
Stop.